Today let us discuss questions related to limit, continuity and differentiability of multivariable functions. So the question 1 says that there is a function given from R2 to R and it is defined as this, and we are supposed to show that d1 f0, and d2 f0, that is partial derivative with respect to x, and d2 is basically partial derivative with respect to y. They have given this information in question exists. So we are supposed to prove that this exists, and further in second part we are supposed to show that function fx comma y is continuous at 0, 0, and that we are supposed to show using epsilon delta method. And in third part we are supposed to show that fx comma y is not differentiable at 0, 0. So let's start with first part of the question. So in that we are supposed to show that d1 f0, 0, that is basically partial derivative of f with respect to x at 0, 0 exists. We are supposed to show this exists, and d2 f0, 0, that is basically partial derivative of f with respect to y at 0, 0. So let us check first d1 f0, 0. So partial derivative of f with respect to x at 0, 0 will be basically limit h approaching 0 f of 0 plus h minus 0 minus f of 0, 0 divided by h, and this thing is equals to limit h approaches 0 f h comma 0 minus f0, 0 divided by h, and this is equals to limit h approaches 0. Now my fh comma 0 will be basically fh comma 0 will be h into 0 square divided by h square plus 0 square. This is basically 0. So we'll get a 0 minus f0 comma 0 is 0 divided by h. So this is basically equals to 0. So from here we can say that d1 f0, 0 exists and is equals to 0. Likewise we can check d2 f0, 0. So that will be basically derivative of f with respect to y at 0, 0, and that will be equals to limit k approaches 0 f0, k plus 0 minus f0, 0 divided by k. This will be equals to limit k approaches 0 f0, k minus f0, 0 divided by k, and this will be equals to limit k approaches 0 f0, k will be basically it will be 0 into k square divided by 0 square plus k square, and this is 0 only. So this limit will be 0 minus 0 divided by k, and this turns out to be 0. So from here we can say that our d2 f0, 0 exists and it is equals to 0. So this completes our first part of the question. In second part they ask us to find fx, y, whether function f is continuous at 0, 0, and we are supposed to check it using the epsilon delta method. So let's do that. So second part says that check continuity of fx, y at 0, 0. So first let us see what is epsilon delta definition of continuity. So epsilon delta definition says that if for all epsilon greater than 0 we got there exists a delta dependent on epsilon which is also greater than 0, such that our mod of fx, y minus fa, b is less than epsilon whenever our mod of x, y minus a, b is less than delta, then we say that our function fx comma y is basically continuous at point a comma b, and we are supposed to check the continuity of function fx comma y at 0 comma 0. So let us assume that epsilon greater than 0 be any arbitrary epsilon, and if with respect to this epsilon we are able to find a delta dependent on epsilon such that these conditions satisfies, then we can say that our function fx is continuous. So let us assume that epsilon is greater than 0, then what will be our mod of fx comma y minus f0 comma 0. So this thing will be basically equals to xy square divided by x square plus y square minus 0, and this thing is basically equals to mod of xy square divided by x square plus y square. Now we know that x square is less than equals to x square plus y square for all y comma x in real line, because in real y square will be something positive always, and adding x square with something positive will always be greater than x square. Likewise y square will also be less than x square plus y square. So and this thing is also true for all xy in reals. So from here we can say that mod of x is less than equals to under root x square plus y square, and mod of y is also less than equals to under root x square plus y square. Now we will be using this mod of x and mod of y herein to simplify our absolute value. So we will be getting mod of fx comma y minus f0 comma 0 equals to mod of xy square divided by mod of x square plus y square, and this thing will be equals to mod of x into mod of y square divided by x square plus y square mod. Now using this and this relation, we'll be getting this as less than equals to under root x square plus y square into under root x square plus y square whole square divided by mod of x square plus y square, and this thing will be equals to x square plus y square mod 3 by 2 divided by mod x square plus y square, and if we simplify it further we'll be getting this as equals to under root x square plus y square, and this must be less than epsilon whenever mod of x comma y minus 0 comma 0 is less than delta. That is, if I use distance formula, I'll be getting under root x square plus y square less than delta. So if I choose delta is equals to epsilon only, then for all epsilon greater than 0 there exists a delta greater than 0 that is basically equals to epsilon only, such that mod of fx comma y minus f0 comma 0 is less than epsilon whenever mod of x comma y minus 0 comma 0 is less than delta. So our function fx satisfies this definition, so we can say that our function fx comma y is continuous at 0 comma 0. So this basically proves the second part of the question, and in the third part we are supposed to show that the function fx comma y is not differentiable at 0 comma 0. So let us do that part as well. So third part says that we are supposed to show that fx comma y that is equals to fxy square divided by x square plus y square when x comma y is not equals to 0 comma 0 and 0 when x comma y is equals to 0 comma 0. So we are supposed to show that fx comma y is not differentiable at 0, 0. So we say that a function fx, y is basically differentiable at x, y if fx, y is differentiable at 0, 0 if one of the partial derivative exists and other partial derivative is continuous at 0, 0, and other partial derivative is continuous at 0, 0. So if any one of the partial derivative is existing and other partial derivative is continuous, then we can say that the function fx, y is basically differentiable at 0, 0. So for that, first let us find out the partial derivative of f with respect to x and y both. So if we find out with respect to x, so it will be basically x square plus y square into y square minus xy square into 2x divided by x square plus y square whole square, and this thing will be equals to x square y square minus y raised 4 minus 2x square y square divided by x square plus y square whole square, and this thing will be equals to, if I simplify it, I'll be getting minus of y raised 4 plus x square y square divided by x square plus y square, and this thing will be equal to, I can take y square as common, so I'll be getting x square plus y square divided by x square plus y square whole square, and this will be equals to minus y square divided by x square plus y square. So this is basically partial derivative of f with respect to x, and now partial derivative of f with respect to y will be basically x square plus y square into 2xy minus xy square into 2y divided by x square plus y square whole square, and this thing will be basically equals to 2x cube y plus 2xy cube minus 2xy cube divided by x square plus y square whole square, and this thing balances this. So our partial derivative with respect to y is 2x cube y divided by x square plus y square whole square. Now we have calculated partial derivative of f with respect to x and with respect to y, and we know that, like from part 1, that both the partial derivative at 0, 0 exists. So we are now supposed to check whether one of them is continuous at 0, 0 or not. So for that, so let us check continuity of this only partial derivative with respect to 0, 0. So if it is continuous, then no matter which path we choose, then it must be continuous throughout. So let us assume that y is equals to mx. Then limit x, y approaching 0, 0, if x, y will be basically equals to limit x approaching 0 if x, y is basically equals to mx. So this limit must exist and should be unique if a function del f by del y is continuous at 0, 0. So let's see what this limit turns out to be. Limit x, 0, 2x cube into y is basically mx divided by x square plus m square x square whole square. So if we simplify it, we'll be getting limit x approaching 0 2m divided by 1 plus m square whole square. So can you see that this limit basically depends on value of m. So if I take m equals to 2, I'll be getting different value of limit, and if I take m equals to 3, then there will be different limits. So a limit of del fy del y is not unique. So from here we can say that del f by del y is not continuous at 0, 0. Likewise, we can show that this del f by del x is also not continuous at 0, 0. So none of the partial derivative is continuous at 0, 0. So from here we can say that our function fx is not differentiable, because it is not meeting the sufficient criteria of differentiability, that is, one of the partial derivative must exist and other must be continuous. Both the derivatives are existing, but none of them is continuous at 0, 0. So we can conclude that our function fx is not differentiable at 0, 0. So this is basically sufficient condition for differentiability. So let's move on to next question. So the next question says that they have given us a function fx comma y, and we're supposed to find basically fxy at 0, 0 and fyx at 0, 0, and we're supposed to show that these two will turn out to be equal. So let us see. So for that, first let's calculate fx 0, 0. So this thing will be basically equals to limit h approaches 0 f0 plus h minus 0 minus f0, 0 divided by h, and this will be basically equals to limit h approaches 0 fh, 0 will be modulus of h square minus 0 square, that is modulus of h square minus f0, 0 is 0 divided by h. So this basically gives me 0 only. Now let us calculate value of fy at 0, 0, and that will be basically equals to limit k approaches 0 f0, 0 plus k minus f0, 0 divided by k, and this thing will be equals to limit k approaches 0 f0, k will be basically modulus of minus k square minus 0 divided by k, and this limit will also be 0. But we are supposed to find out limit of f xy 0, 0. So this thing will be basically equals to limit h approaches 0 fy 0 plus h minus 0 minus fy 0, 0 divided by h, and this thing is equals to limit h approaches 0 fy h, 0 minus fy 0, 0 divided by h. So we know what this limit is, that is fy 0, 0 from here, but we don't know what is fy h, 0. So let us find out this value as well. So fy h, 0 will be basically equals to limit k approaches 0 f h, 0 plus k minus f h, 0 divided by k, and this will be basically equals to limit k approaches 0 f h, k minus f h, 0 divided by k. And if I calculate f h, k will be basically equals to limit k approaches 0 modulus of h square minus k square minus modulus of h square divided by k. So this is my value of f h, h, 0. Now if I take limit k approaches 0, it will be basically equals to is we are taking our k to be approaching 0, so h square minus k square will be basically h square minus k square only, and minus h square divided by k. So this also gives us limit as 0. So we got fy h comma 0 as 0. Now if we substitute this limit here, so we'll be getting fx comma y 0 comma 0 as limit h approaching 0, 0 minus 0 divided by h. So that gives us fx comma y as 0 only. Now let us calculate fy comma 0. fyx 0 comma 0. So this will be equals to limit k approaches 0, fx 0 comma k minus fx 0 comma 0 divided by k. Now we know what this limit is, but we don't know what is fx 0 comma k. So let us calculate that. So fx 0 comma k will be basically equals to limit h approaches 0, f0 plus h comma k minus f0 comma k divided by h, and this thing will be equals to limit h approaches 0, fh comma k minus f0 comma k divided by h, and this thing will be basically equals to limit h approaches 0 modulus of h square minus k square minus modulus of minus k square divided by h, and this thing will be equals to minus h square minus k square minus k square divided by h, and this thing is minus h square plus k square minus k square divided by h, and limit h approaches 0. So this limit also turns out to be 0. So our limit if x comma y at 0 comma 0 is basically, sorry, fy comma x we are calculating. So that is basically fyx at 0 comma 0 is limit k approaches 0, 0 minus 0 divided by k, and that turns out to be 0. So our limit fxy at 0 comma 0 is same as fyx at 0 comma 0, and this is what we are supposed to show in this question. Yeah, we are supposed to find these limits, and further we are supposed to conclude that both these limits are equal only. So let's move on to next question. So the next question says that f is a function from D, that is basically subset of R square, to R, and a comma b belongs to D. So f is a function of D to R, where D is basically subset of R square, and a comma b basically belongs to D, that is a comma b is a point inside the subset D, and it is given that fx comma y is continuous at a comma b. fx comma y is continuous at a comma b. This information is given to us, and we are supposed to show that function fx comma b and fa comma y are continuous at x equals to a and at y equals to b respectively. So this is a very basic question. So in that what they have done is they have given that a multivariable function is continuous at a comma b, and further they have taken one of the variables turn by turn. First they have taken y as constant, that is b here, and in again they have taken x as constant, that is a, and then we are supposed to show that these functions are also continuous. Basically they have turned multivariable function into one variable turn by turn, and then we are supposed to show that these are continuous at respective points. So let's first write down that what is definition of continuity of function in epsilon delta form, and then we will proceed. So epsilon delta, since fx is continuous at a comma b, that means limit of fx comma y as my x comma y approaches a comma b is basically equals to fa comma b. So if I write it in epsilon delta format, so I'll be getting for all epsilon greater than 0 there exists delta basically dependent on epsilon, and that delta is also greater than 0 such that modulus of fx comma y minus fa comma b is less than epsilon whenever norm of x comma y minus a comma b is less than delta. So we are supposed to show that basically our claim is fx comma b is continuous at x equals to a and fa comma y is continuous at y equals to b. So since if I see my definition of continuity, that is for all epsilon greater than 0 there exists delta greater than 0 such that modulus of fx comma y minus fa comma y b is less than epsilon whenever x comma y minus a comma b is less than delta. And this thing is true for all x comma y, in real number. But if I take specifically my y to be b, then also it must hold. So let us take our y as b. So what I will be getting is modulus of fx comma b minus fa comma b is less than epsilon whenever modulus of x comma b minus a comma b is less than delta. So can you see that for all epsilon for which this holds, we got f of x comma b minus f of a comma b less than epsilon. So this basically tells us that f of x comma b is continuous at y equals to at x equals to a. Likewise, if in this definition I choose my x as equals to a, then I can show that the function f of a comma b, function f of a comma y is basically continuous at y equals to b. So let's name this definition as 1. So from here in 1, if I choose my x equals to a, so I'll be getting modulus of f a comma y minus f a comma b is less than epsilon whenever modulus of a comma y minus a comma b is less than delta. So this basically shows that f of a comma y is continuous at y equals to b. So from here we can conclude that if a multivariable function is basically continuous at a point, then it is also continuous at some if we convert that function into one variable function by choosing one of the variables as constant, then also the continuity holds. So this basically proves that. So let's move on to next question. So the next question says that show that the function this is basically continuous and differentiable at 1 comma minus 1. So the function fx comma y is basically given to me as x square minus y square divided by x minus y when x comma y is not equals to 1 comma minus 1 or 1 comma 1, and it is 0 when x comma y is equals to 1 comma 1 or 1 comma minus 1. So if we see basically epsilon delta definition, so for that, for all epsilon greater than 0 we must find a delta greater than 0 such that f of x comma y minus f of 1 comma minus 1 must be less than epsilon whenever mod of x minus 1 modulus of x comma y minus 1 comma minus 1 is less than delta. So let us assume that there is an epsilon greater than 0 and it is an arbitrary epsilon. So mod of fx comma y minus f of 1 comma minus 1 will be basically equals to x square minus y square divided by x minus y minus f at 1 comma minus 1, that is 0 only. So this is basically equals to x square minus y square divided by x minus y, and this must hold whenever this relation holds. That is basically this must hold whenever modulus of x minus 1 square plus y plus 1 square is less than delta basically. So if I simplify it, I'll be getting modulus of x minus y into x plus y divided by x minus y. So this balances this, so we are left with this is equals to modulus of x plus y. But we are supposed to find a relation where this thing is less than delta. So to get this, what I'll be doing is I'll just add and subtract 1 basically in this. So this basically gives me this thing as equals to modulus of x minus 1 plus modulus of 1 plus y. And we know that modulus of x plus y is basically less than equals to modulus of x plus modulus of y, basically the triangle inequality. So if I apply that, I'll be getting modulus of x minus 1 plus modulus of y plus 1. And we have seen a relation that mod x is less than equals to under root x square plus y square, and likewise mod y is less than equals to under root x square plus y square. So from here we can conclude that modulus of x minus 1 is less than equals to x minus 1 square plus y plus 1 square, and modulus of y plus 1 is less than equals to under root x minus 1 square plus y plus 1 square. So if I use these relations here, so I'll be getting modulus of fx comma y minus f1 comma minus 1 is less than equals to 2 times under root x minus 1 square plus y plus 1 square, and this thing must be less than epsilon, and this thing holds whenever modulus of x minus 1 square plus y plus 1 square is less than epsilon by 2. So we can choose our delta as epsilon by 2. So for delta equals to epsilon by 2, this thing holds, and for this delta, this fx comma y minus f1 comma minus 1 is less than epsilon. So this basically proves that fx comma y is continuous at 1 comma minus 1. So I have seen this basically proves continuity at 1 comma 1. So I have seen many solutions which basically use this definition, limit x comma y approaches a comma b, fx comma y equals to f a comma b to prove continuity. But that is not a correct way to approach this. This basically using epsilon delta method is basically the correct way to show a continuity. You can use this definition to discard that it is continuous at some it is not continuous at some specific point. So to prove continuity, you must restrict to showing continuity using epsilon delta definition only. So let us check its differentiability at 1 comma minus 1. So we have seen that sufficient condition for differentiability is basically a sufficient condition for differentiability is to show is basically that one of the partial derivative exists exists and other is continuous. At point 1, -1, because this is the point where we are supposed to check the differentiability. So the function fx, y is basically given to me as x square minus y square divided by x minus y, and 0 when x, y is basically 1, -1 or 1, 1, or when x, y is not equals to 1, -1 and 1, 1. So to check, let's find out. We can simplify it to write it as x plus y, and here x plus y is not equals to 1, -1 or 1, 1. Likewise 0 when x, y is equals to 1, -1 and 1, 1. So if you take its partial derivative with respect to x, so you'll be getting 1, and if you take its partial derivative with respect to y, again you'll be getting 1. So you can see that both the partial derivatives exist, and since it is we are getting a constant thing, so both are continuous at, both exists and are continuous at 1, -1. Sorry. Yeah, both the partial derivative are continuous at 1, -1. So from both these things we can conclude that fx, y is differentiable at 1, -1. Yeah, so that's it. This proves this question. We're supposed to show that it is continuous and differentiable only. So let's move on to next part. So the next question says that they have given us a function fx, y, that is basically x, y square if our y is greater than 0, minus x, y square if our y is less than equals to 0, and we are supposed to determine del f by del x at point 0, 1 and del f by del y at 0, 1. We are supposed to check with which one of these exists and which does not exist. So let us do that. So let's first calculate del f by del x at 0, 1. It will be limit h approaching 0 f0 plus h, 1 minus f0, 1 divided by h, and this thing will be basically equals to limit h approaching 0 f h, 1 minus f0, 1 divided by h, and this will be equals to limit h approaching 0 fh, 1 is basically h minus f0, 1 will be 0 only divided by h. So this limit is equals to 1. So this limit exists and it is equals to 1 only. Likewise, if we find del f by del y at 0, 1, it will be limit k approaching 0 f0, 1 plus k minus f0, 1 divided by k, and this thing will be equals to limit k approaches 0 f0, 1 by k will be basically equals to 1 plus, that is 0 only, 0 minus 0, so it is basically 0 minus 0 divided by k, that is equals to 0 only. So both of them exist but they are not equal, so both del f by del x and del f by del y exists at 0, 1. So we are supposed to check their existence only in this question. So let's move on to next question. So the next question says that they have given us a multivariable function fx, y, and we are supposed to show that fx, y is not equals to fy, x at 0, 0. So fx, y is basically equals to xy into x square minus y square divided by x square plus y square whenever x square plus y square is not equals to 0, and 0 whenever x square plus y square is equals to 0. So for that, first we must calculate partial derivative of f with respect to x, and then partial derivative of x with respect to y. So del fx at 0, 0 will be basically equals to limit h approaches 0 f h, 0 minus f 0, 0 divided by h, and this thing will be equals to limit h approaching 0 fh, 0 will be 0 minus 0 divided by h, and this thing turns out to be 0. Likewise, if we calculate fy 0, 0, so this will be limit k tending to 0 f0, k minus f0, 0 divided by k, and this will be equals to limit k approaches 0 f0, k will be 0 minus 0 divided by k, and this thing is also 0. Now we will also be needing a partial derivative of fx 0, k. So let's calculate that. Limit h approaching 0 fh, k minus f0, k divided by h, and this thing will be equals to limit h approaching 0 fh, k will be basically equals to hk into h square minus k square divided by h square plus k square minus f0, k will be 0, and this thing is divided by h. So this will be equals to limit h approaches 0. This h balances this, so we are left with k into h square minus k square divided by h square plus k square. So if we take h approaches 0, so we will get this limit as minus of k. Likewise, let us calculate limit of fy at h, 0. So this thing will be basically equals to limit limit k approaches 0 fh, k minus fh, 0 divided by k, and this will be equals to limit k approaches 0 hk into h square minus k square divided by h square plus k square minus fh, 0 will be 0 and divided by k. This k will balance out this, so we'll be left with limit k approaches 0 h into h square minus k square divided by h square plus k square. So if we'll take k approaches 0, this limit will be equals to h. Now let us find out fx, y and fy, x. So fx, y at 0, 0 will be basically equals to limit h approaching 0 fy h, 0 minus fy 0, 0 divided by h, and this will be basically limit h approaches 0. We have already calculated fy h, 0, that is equals to h, and fy 0, 0 that is 0 divided by h. So this limit turns out to be 1. So from here we got fxy 0, 0 as 1. Now let us find out fyx 0, 0. So this will be equals to limit k approaches 0 fx 0, k minus fx 0, 0 divided by k, and we have already solved this fx 0, k, that is minus of k. So it will be limit k approaches 0 minus k minus 0 divided by k. So this limit turns out to be negative of 1. So you can clearly see that negative 1 is not equals to 1. So fyx at 0, 0 is not equals to fxy at 0, 0, and that's what we are supposed to prove in this question. So let's move on to next question. So the next question says that they have given us a function fx, y as this, and we are supposed to calculate this at 0, 0. So this is the same question that we have done, like this question only, both are same questions. So this one is a repeated question. Let's move on to the next question. So the next question says that this is a function f x comma y as this, and we are supposed to find a delta such that this thing is less than this. So in this question what they have done is, so like using the definition of continuity, we are supposed to find a delta for a specific epsilon. So they have given us epsilon as 0.01. So for this specific epsilon we are supposed to find a delta such that this thing holds. That is, like for this epsilon we need a delta so that this function fx is basically continuous whenever this is also true. So like in the actual question here they have given is fx comma y less than 2x raised 4y minus 5x square y square plus y raised 5 divided by x square plus y square whole square whenever x comma y is not equals to 0 comma 0, and it is 0 whenever x comma y is basically equals to 0. So this was the actual question, but you won't be able to solve this. So like there might be slight misprint in this question. So what you can do is, like either you can take here x cube, like either you can take this term as negative of 5x cube y square, or you can take it as negative of 5x square y cube and then solve. So for time being we'll be taking this and we'll solve it for specific epsilon, and you can see calculate it using this term as well. It depends on you, whichever you want to take you can take that. So we are supposed to find a delta such that mod of fx minus y minus f0 comma 0 is less than epsilon whenever under root x square plus y square is less than delta. So we are supposed to find this delta when our epsilon is 0.01. So let us solve it. So we'll be getting f of x comma y is 2x raised 4y minus 5x cube y square plus y raised 5 divided by x square plus y square whole square minus f0 comma 0 is 0 only. So this basically turns out to be less than equals to, we are basically using a triangular inequality that basically gives us this term less than 2 modulus of x raised 4 by y divided by x square plus y square whole square plus 5 into x cube y square divided by x square plus y square whole square plus modulus of y raised 5 divided by x square plus y square whole square. So we have already seen that modulus of x and modulus of y are basically less than x square plus y square. So we'll be using this thing here. So from here we'll get, if I simplify it, I'll be getting x raised p into mod of y raised q will be basically less than equals to x square plus y square raised p plus q divided by 2. So from here we'll get mod of fx comma y minus f0 comma 0 less than equals to 2 into, here it is x raised 4 into y, so that basically gives us x square plus y square raised 5 by 2 divided by x square plus y square raised 2 plus 5 into, again we'll be getting x square plus y square raised 5 by 2 divided by x square plus y square whole square plus x square plus y square raised 5 by 2 divided by x square plus y square whole square, and this term is equals to 5, 6, 7, 8 times x square plus y square raised 5 by 2 minus 2. That is basically equals to 8 into under root x square plus y square, and according to definition this term must be less than equals to epsilon, that is 0.01. So from here we got under root x square plus y square must be less than 0.01 divided by 8. So, and this is basically our delta, like for the given epsilon, delta is equals to epsilon by 8, that is 0.01 divided by 8. Like even if they ask us for some other epsilon, then also we can just substitute this value of epsilon here and solve for that as well. So delta is basically equals to 0.01 divided by 8, and that is greater than 0. So for epsilon equals to 0.01, there exists delta equals to 0.01 divided by 8, such that mod of fx comma y minus f0 comma 0 is less than 0.01 whenever delta, that is 0.01 divided by 8, is basically greater than mod of x square plus y square. So that's all we are supposed to do in this question. So the next question says that examine the continuity and differentiability of this function. So we are supposed to check its continuity and differentiability. So let us do that. So if you see that our function fx comma y is basically x square minus x under root y divided by x square plus y whenever x comma y is not equals to 0 comma 0, and it is 0 when x comma y is equals to 0 comma 0. So let us solve it. So if I solve it, like if you see that if I take my y equals to m of x square, then if you see that it will be x square minus x square under root m divided by x square plus x square into m, and it will turn out to be dependent on m basically. So that basically gives us idea that this won't be continuous. So let us do it formally. So to disprove it, we'll be using this, that x comma y whenever approaches 0 comma 0, fx comma y is, if it is continuous, then this thing must hold. So if we can show that there, like for some path there exists a path for which this doesn't hold, so we'll be good to go. So let us assume that y is equals to m times of x square. So our limit x comma y approaching 0 comma 0, fx comma y basically be equals to limit x approaches 0, fx comma mx square. So this limit will be equals to limit x approaching 0, fx comma mx square will be basically x square minus x under root mx square divided by x square plus y, that is mx square, and this will be equals to limit x approaching 0, x square minus x square under root m divided by x square plus mx square. So if I take its limit, I'll be getting limit x approaching 0. I can take x square common from numerator. It will be 1 minus under root m divided by x square 1 plus m, and this x square balances this. So our limit reduces to 1 minus under root m divided by 1 plus m. So this limit is basically dependent on m, so we didn't get a unique limit. So if we choose different path, we'll be getting different limits. So this basically shows that function fx comma y is not continuous at 0 comma 0, and we know that continuity is necessary condition for differentiability. So since it is not continuous and continuity is necessary condition for differentiability, so from here we can conclude that fx comma y is not differentiable at 0 comma 0. So now let us move on to next question. So the next question says that compute fx comma y at 0 comma 0 and fy comma x at 0 comma 0, and further discuss the continuity of fx comma y and fy comma x at 0 comma 0. So let us do that. So our fx comma y is given to us as x y cube divided by x plus y square whenever x comma y is not equals to 0 comma 0 and it is 0 whenever x comma y is equals to 0 comma 0. So we are supposed to compute this. So for that, first let us calculate fx 0 comma 0. That will be limit h approaching 0 fh comma 0 minus f 0 comma 0 divided by h, and this thing will be equals to limit h approaches 0 fh comma 0 will be 0 minus 0 divided by h. So this limit is 0 only. Likewise we can compute fy 0 comma 0. That will be limit k approaching 0 f0 comma k minus f0 comma 0 divided by k, and this thing will be equals to limit k approaching 0 f0 comma k will be 0 only and f0 comma 0 is 0. So this also turns out to be 0. Now let us calculate fx comma y 0 comma 0. So this will be equals to limit h approaching 0 fy h comma 0 minus fy 0 comma 0 divided by h, and this thing will be equals to limit h approaching 0 fy h comma 0 will be basically, so we supposed to find out this limit as well. So fy h comma 0 will be equals to limit k approaches 0 fh comma k minus fh comma 0 divided by k, and fh comma k will be hk cube divided by h plus k square minus 0 fh comma 0 will be 0 only and divided by k. So the limit will be 0 only. So if I further find out fx comma y 0 comma 0, this will be limit h approaches 0 fy h comma 0 is 0, so it is 0 minus 0 divided by h. So this limit turns out to be 0 only. Likewise if I find fy x 0 comma 0, so that will be limit k approaches 0 fx 0 comma k minus fx 0 comma 0 divided by k, but this limit, that is fx 0 comma k, will be limit k approaches 0 and this limit is limit h approaches 0 fh comma k minus fh f0 comma k divided by h minus fx 0 comma 0 divided by k, and this will be basically equals to limit k approaching 0 into inside will be limit h approaches 0 h comma k will be h k cube divided by h plus k square minus 0 comma k will be 0 divided by h minus this is 0 and whole thing divided by k. So it will be limit k approaches 0, and if we solve it we'll be getting k. This limit will be, this h will balance out this, and if we take limit h approaches 0 we'll be getting k minus 0 divided by k. So this limit turns out to be 1. So from here we get fx comma y 0 comma 0 is not equals to fy comma x 0 comma 0. So we are supposed to compute this, and further question also asks us to discuss the continuity of fx comma y and fy comma x at 0 comma 0. Like we are supposed to check continuity of fxy and fyx. You can conclude that from here also, but like if you just solve it for yourself, then like if you do it by just calculating values. So if I calculate fx, so I'll be getting x plus y square into y cube minus xy cube divided by x plus y square whole square, and this thing will be equals to y raised 5 divided by x plus y square whole square. And if I calculate fx yx, so that will be basically equals to taking a derivative with respect to y into 5y raised 4 minus y raised 5 into 2 x plus y square into 2y divided by x plus y square raised 4. And from here I can just balance out one term, so it will be x plus y square into 5y raised 4 minus 2 to the 4y raised 6 divided by x plus y square cube. So this term is basically equals to 5xy raised 4 plus 5y raised 6 minus 4y raised 6, that is y raised 6 divided by x plus y square cube, and this thing is equals to, if I take y square common, y raised 4 common, so I'll be getting 5x plus y square divided by x plus y square cube. Now if I take, like here, if I take, let me just reduce its sizes and then we can discuss. So like if here I take my x as equals to my square, so this, that is fyx will reduce to basically y raised 4 into 5y square plus y square and m also, and it is my square plus y square cube. So it will be basically equals to y raised 6 into 5m plus 1 divided by m plus y cube into y raised 6, and this balances out this. And if we take its limit, like whenever y approaches 0, because we are supposed to check its continuity at 0, 0, and we have assumed x to be this, so it will basically reduce to limit y approaches 0, and here also limit y approaches 0. So from here you will keep getting that limit is basically dependent on value of m, that is limit is not unique. So from there we can all say that it is not continuous. So like this way you can also do, or you can conclude from here also, because there is a theorem that if it is continuous then also they are equal at that specific point. I couldn't recall the exact theorem what it is, but it is somewhat like this. So let's move on to next question. So the next question says that, or we can just stop the video here and we'll discuss other questions in next video, because otherwise the video will be too long to upload. So thank you for watching, and if you're liking the content then please like, share and subscribe the channel, and also help me spread the word about the initiative. Thank you.